The fastest AI chip can still spend most of its time waiting for model weights to arrive from memory, waiting for another accelerator across the rack, waiting for the previous token because language is generated one step at a time. That is the hardware bottleneck behind inference. And it changes the question. This is not simply a contest between a powerful GPU and a cheaper custom chip. It is a contest between two systems for moving data, keeping compute occupied, and serving a response before the user leaves. One correction first. NVIDIA does not sell an H300. The system that fits this comparison is the GB300 NVL72, a Blackwell Ultra rack. Across from it sits bespoke silicon such as Microsoft's Maya 200 and Google's Ironwood TPU raw power against architectural precision. But to choose a winner, we need to define what winning means. An LMA request has two different physical phases. First comes pre-fill. The system reads the prompt and processes many input tokens in parallel. This rewards batching and wide matrix engines. Then comes decode. The model emits one token, feeds that result back, and only then produces the next. At every step, billions of weights may move through high bandwidth memory again. That is why decode is often memory bandwidth bound. The tensor cores have arithmetic available, yet sit underfed. Longer contexts add the key value cache, which grows with the sequence and competes for capacity and bandwidth. Now the scorecard becomes clearer. Time to first token measures the weight before the answer begins. Time per output token measures the rhythm after it starts. Throughput measures how much the system serves together. A huge batch can raise throughput while one person waits longer. Peak flops alone cannot tell you which system feels fast. NVIDIA attacks the problem at rack scale. A GB300 NVL72 joins 72 Blackwell Ultra GPUs with 36 Grace CPUs. NVIDIA lists 20 terabytes of GPU memory, up to 576 terabytes per second of aggregate memory bandwidth, and 130 terabytes per second across NVLink. The goal is a tightly connected machine that can hold enormous models, split experts across GPUs, and keep communication inside one fast domain. That flexibility is the GPU argument. CUDA, TensorR, TLM, PyTorch, and broad libraries let operators move from vision to a new reasoning model without redesigning silicon. The rack can train, fine-tune, and infer. But flexibility has a physical bill. NVIDIA says the complete liquid-cooled rack can require up to 142 kilowatts. If traffic is irregular or software leaves GPUs underused, raw capacity becomes stranded capital. Custom silicon starts from the opposite direction. Instead of supporting almost every workload, the designer studies production models and removes what they do not need. Microsoft's Maya 200 is built for inference. Each chip combines more than 10 petaflops of 4-bit compute with 216 gigabytes of HBM3E at 7 terabytes per second, plus on-chip SRAM and dedicated data movement engines. Its stated SoC envelope is 750 watts. Ironwood uses the same principle, layered memory, and a topology built around TensorWork. The promise is architectural precision, more useful token work per watt, and tight co-design between model, compiler, network, and chip. But specialization creates another bottleneck: software. Kernels must map well. Quantization must preserve accuracy. New models need compiler support. A change that runs tomorrow on a GPU may take months to tune on an ASIC. Efficiency pays only when workload scale and stability repay that engineering cost. So, which side wins latency and throughput? There is no honest universal number yet. A GB300 rack and a Maya chip are different system boundaries, while vendor claims use different models, precisions, batch sizes, sequence lengths, power definitions, and software. Dividing peak bandwidth by chip power looks scientific, but it compares a SoC envelope with a liquid-cooled rack and ignores hosts, switches, cooling, and utilization. A fair test freezes the model: accuracy target, input length, output length, precision, software, and concurrency. Then it records 4 lines together, 99th percentile time, to first token, time per output token, sustained tokens per second, and complete system wall power. ML Commons separates these concerns. Its DeepSeek R1 server test constrains responsiveness while measuring throughput, so a system cannot win by building a giant queue. Until bespoke accelerators publish directly comparable results, the verdict is conditional. GPUs dominate breadth and changing frontier models. Custom silicon can dominate predictable inference at hyperscale. Does custom silicon make the standard data center obsolete? No. It changes what a standard data center contains. The likely winner is a heterogeneous fleet. GPU racks absorb new models, research, fine-tuning, and bursty demand. Custom accelerators handle stable, high-volume services where every saved joule repeats billions of times. Smaller, purpose-built chips move inference closer to users when latency, privacy, or network cost matters. A scheduler becomes the strategic layer, routing prefill, decode, retrieval, vision, and speculative draft work to different engines. That is the 2026 shift, not one chip replacing every other chip, but the fracture of one-size-fits-all computing. The GB300 wins when flexibility, memory scale, and mature software are worth the power. Bespoke silicon wins when precision, utilization, and volume outweigh portability. The winning architecture is the one that wastes the least motion of data, energy, money, and engineering time for the workload actually being served.